Hello, everyone. Thanks very much for inviting me to the APMM conference. So my name is Dr. Sharidya Rahman. So I'm one of the research fellows here at Monash University in Melbourne, Australia. And I'm very delighted to be part of this conference and giving a keynote talk about our recent research since last year and also this year. So today I'll be talking mostly about phonon dynamics and interlayer excitons in twisted two-dimensional Moiré heterostructures. So we had some recent publications on the 2D materials, and we investigated the phonon dynamics based on the interlayer twist, and also based on the and also we investigated the effect of dielectric screening on the effect of dielectric screening on those 2D materials, and we saw how that affected the interlayer excitons as well. Okay, so I'll start sharing pointer options. So this is a short outline of the talk today. So primarily I'll be talking about some motivation and background. So we'll talk about some interlayer excitons in van der Waals heterostructures, and then we will see how it differs from the Moiré superlattice and how that actually affects excitons and the dipolar excitons as well. And we'll see some examples of more imaging of some Moiré superlattice. Then we'll be talking then I'll be just briefly be introducing our last year work on the phonon dynamics of twisted TMD heterostructures. And then eventually we're talking about suspended and freestanding heterostructures that actually gave a higher collection efficiency or formation efficiency of interlayer excitons at room temperature. And then we'll end the talk with some minor visions on interlayer excitons and more heterostructures as to how they can be useful in several applications on a day-to-day basis. So primarily, I would like to start off by showing some applications of the interlayer excitons for future low-energy electronics. So over here, this diagram or this schematic is indicating a transistor or a heterostructures actually. So in a heterostructure, there are two layers, and one of the layers there is a flow of electrons, and the other layer there is a flow of holes. So these electrons and holes, they can combine together to form an exciton pair, right? And this exciton pair can actually can flow across those two layers to form an electric current. So when it is an interlayer excitons which means electrons in our one layer and the holes are in the other layer, then it means that the current flowing through this particular transistor or this particular heterostructures is a electric current composed of interlayer excitons. Now the variations now actually this interlayer excitons can actually lead to the formation of superfluid structures. So that it means these interlayer excitons can flow with almost zero resistance, and as a result, it has a lot of applications in computing and data storage and a lot of other applications. So that's actually one of the key reasons behind a lot of studies behind these interlayer excitons, where this and so in this kind of interlayer excitons are pretty new or like has been investigated in 2D materials for a while, but this kind of interlayer excitons has already been demonstrated in 3-5 semiconductors. For instance, in gallium arsenide and then gallium arsenide heterostructures or quantum well system. So these interlayer excitons are usually formed because of the band gap and due to the band gap at the heterostructure formation, where the electrons are residing in one layer and the holes are residing in another layer. A major drawback actually in these 3-5 quantum well system or 3-5 system was that these interlayer excitons has very low efficiency at room temperature, and this is because of their binding energies, which are actually very low in the order of millieVs. And as a result, in these kind of 3-5 semiconductors or quantum well systems, these kind of interlayer excitons could only exist at very cryogenic temperatures, which is like around 5 Kelvin or a few kelvins, etc. So as a result, this was a major drawback in this kind of 3-5 semiconductors. considering considering the drawbacks on those systems, so this brings us to the 2D materials. So nowadays, these days, people can actually grow this kind of 2D materials or 2D crystals, and eventually they can exfoliate them down to monolayers or bilayer systems. And so this is an example taken from a science paper or a physical review paper where people are able to exfoliate this kind of WaC2 and MoAC2, and they're eventually able to combine them together into to form a twisted TMD heterostructures. And as a result, they're able to emit, and as a result, they're able to and when they actually probe the 2D heterostructure, they were able to see Interlayer Exciton emission at low energy. Now, considering this, so if we take this example, so MoAC2 and WaC2, there is a normal intralayer exciton emission from WaC2 and MoAC2 at room temperature as well. But when it comes to the heterostructures, which is comprising of monolayer molybdenum diselenide and tungsten diselenide, there is an emission at a low energy. So this kind of interlayer excitons is a combination of electron and hole residing in another pair and residing in different layers. So for instance, when in this kind of interlayer excitons can actually form if we say excite the MoAC2, then the then the electrons can combine with the holes from WaC2 and form interlayer excitons. And let's say if we excite a WaC2, then the electrons can jump over and combine with the holes and then eventually form interlayer excitons as well. So this kind of spatially interlayer excitons has a very strong binding energy. It's in the order of about 100 to 200 millielectron volt, which is compared to those 3,5 nitride systems are very high. So, and it also has a very longer lifetime in nanoseconds and picoseconds, nanoseconds and microseconds, which actually provides the major benefit for these materials and this platform as well. So another interesting point about this kind of interlayer excitons is the dipole-dipole interaction, because since these interlayer excitons have vertically oriented dipoles, they can be controlled externally. So let's say using an electrical impulse or using electrical stimulation. And as a result, this gives us more application into increases the application of this kind of 2D materials-based interlayer excitons into multiple quantum phases or multiple systems. So another interesting phenomena is the formation of the Moiré superlattice. So of course, previously we saw that the interlayer excitons can actually form when electrons and holes are residing in another layer. So previously, when people see that when people stack two different monolayers of TMDs, let's say tungsten disulfide and molybdenum disulfide, it can actually form this kind of Moiré superlattice. So Moiré superlattice is basically so when two layers are combined together, it can actually form a periodic pattern, and this periodic pattern is basically called a Moiré pattern. So usually in a Moiré pattern, this can actually lead to the formation of an energy barrier or a pattern that can actually trap an interlayer exciton, which can actually trap an electron hole pair. And this electron hole pair can eventually lead to the formation of Moiré excitons or Moiré interlayer excitons. So these Moiré interlayer excitons are usually high in binding energies. So as a result, this increases the formation efficiency of these at room temperature. So usually in interlayer excitons, there are usually in a Moiré superlattice, there are three regions: region A, region B, and region C. So each of these regions vary slightly in the region very slightly. For instance, this diagram shows a top view of this region A, B, and C. And this is a simulated figure taken from one of the nature publications. So the major difference between the three regions is the vertical of the interlayer distance. So the interlayer distance in region A is the highest, and interlayer distance in region C is the lowest. And as a result, this is able to trap electron and hole pairs at different energy levels. So, and usually this electron hole excitons formed by this electron hole pair have a very strong binding energy of up to even 200 millielectron volt. So this is one of the major factors behind the formation of the collection efficiency of these interlayer excitons. So this is just a quick background on the Moiré superlattice, and usually this Moiré superlattice has been studied in a lot of details in the last decade or in the last 4 or 5 years, and a lot of Nature publications has been carried out as well. Now these Moiré interlayer excitons are highly sensitive to the interlayer twist angle, right? So when the two layers are stacked together, there is a interlayer twist angle in between them. So this kind of interlayer exciton formation efficiency can be altered by the interlayer twist angle as well. For instance, if the interlayer twist angle is increased, then the collection or the formation efficiency of the interlayer twist angle is reduced. And this is because with increasing twist angle, in the Brillouin zone, the k-space orbital becomes indirect, and as a result, their formation efficiency is reduced as well. So recently, a lot of papers or a lot of work has actually started viewing this kind of more superlattice. They use this kind of high resolution technique like SEM or transmission electron microscopy to actually see this kind of more superlattice, and they can be easily be visualized in different domain formations or different more pattern formations. And in addition, people has also used electrical techniques as well. Like for instance, over here, the authors have used conductive mapping or conducting AFM mapping to visualize this kind of periodic Moiré potentials or Moiré traps. And as a result, for instance, this was investigated in MOS2 and WS2 as well. So based on this motivation, recently we worked on WS2 and WSE2 heterostructures. So we saw very interesting phonon dynamics in this kind of twist-dependent heterostructures as well. So we exfoliated WS2 and WSE2, and then we did make a heterostructures using the dry exfoliation technique, and introduced a small interlayer twist angle in between them. And then we were able to control, and then we fabricated many samples with different interlayer twist angles. So this is an example of optical image. This is an example of of a sample fabricated using a WSE2 and a WS2. And we saw a very nice control of the phonon peaks. For instance, this is the E peak of WS2, and it shows a very sensitive very sensitivity to the interlayer twist angle. So similarly, at low temperature as well, we saw a very large deviation of this phonon peaks, and it also showed a very large deviation compared with the twist angle as well. So these kind of fundamental studies on this kind of TMD-based heterostructures has not been studied before. So this was also from the same paper where we have investigated the E peak of WS2, and eventually we tried to compare the first order linear coefficient in this materials. So we did a temperature dependent Raman spectroscopy, and we did a linear fitting. So from there we were able to extract the Chi-T, or the first order linear coefficient, and from there we were able to extract the first order linear coefficient of E peak and also the A peak of both WS2 and WSE2. So this is the one that of the E peak, which is basically the vertical motion of the phonons of the atoms, and this showed also a very nice, also a very high sensitivity to the twist angle as well. So, based on the twist angle, we can actually design systems. For instance, if you want to have very high first order linear coefficients, then you can design a system based on 3-degree twist. And for instance, if you want to have a system where we want to have a very low thermal conductivity or a low first order linear coefficient, then we can use, say, twisted TMDs with a high twist angle as well. So this kind of fundamental studies actually gives us a platform to do a lot of device development as well. So this was the temperature dependent Raman spectrum from the WSE2 side, which is from 240 to 280 wave number. And we also saw at different twist angles, especially at the near zero regime. The phonon peak showed a very nice dependence on the twist angle at low temperature as well, and from there we were able to see a very nice enhancement of the E peak at about, say, 3 degree or 8 degree as well. So this shows that the interlayer twist of the stacking angle is highly sensitive, and the phonon signatures are very sensitive to the twist angle as well. And Raman spectroscopy help us to reveal this kind of interlayer twist, reveal this kind of intruding phonon dynamics in this kind of twisted TMD heterostructures as well. So secondly, so this was a recent publication, and then eventually we were also investigating or interested in Moiré excitons as well. Now there has been evidence of Moiré excitons as well. For instance, in this particular works taken from Nature, people has already shown the formation has shown the formation of interlayer excitons at low wave number at low energy as well. However, one of the major drawback was that they had to encapsulate these materials with hydrogen boron nitride. So that otherwise and as a result, because of the stability as well, and due to the encapsulation, the formation efficiency of these IX has decreased because of the increase in dielectric screening. So this was a major drawback in these systems as well. So in order to actually work around or to find a solution around that, so one of the recent publication was working on this, increasing the formation efficiency of IX at room temperature. So we fabricated silicon dioxide substrate with trenches, and then we mechanically transferred heterostructures of WSE2 and WSE2 on a supported side and on a suspended part as well. So this part shows that the heterostructure is supported on a silicon dioxide, and this part is where it is suspended or freestanding, and as a result, it is able to experience a reduced dielectric screening. So this is actual optical image of sample fabricated. So as you can see, this is the PL spectrum from this kind of suspended to TMD heterostructures. And so if we look at closely, then WSE2 of course shows high energy intralayer excitons. But if you look closely at low energy, we have a formation of IX at room temperature, which is coming only from the suspended part and not from the supported part. So if you look closely into this particular energy regime from 1.35 to 1.5, and then if we do some fitting, we can see there is a formation of 3 different kind of interlayer excitons at room temperature, which is only coming from the suspended part and not from the supported part. This was mainly attributed to the reduction of the dielectric screening, and as a result, this was able to increase the formation efficiency of these interlayer excitons as well. So the twist angle of this was near to 0, and with the Moiré period of about 7.9 nanometers. So the reason was because of 3 different peaks that are noticed, because as we explained before, that the Moiré superlattice actually forms 3 different regions, like A, B, and C, and it is able to trap electron and hole pairs at different energies. So as a result, we were able to obtain different IX1, IX2, and IX3. But another reason was there was also assigned to the spin orbit difference in the spin orbit coupling of the conduction band and the valence band that actually resulted in the formation of IX at different energies. So, so as we understand, this kind of interlayer excitons are very interesting, and they have been investigated very heavily in the last few years. So this kind of interlayer excitons are very important for the formation of superfluidic structures or superfluidity. So superfluidity basically can be visualized or envisioned as say cars flowing on a traditional road. So cars on a normal road with high traffic cannot move and it's very slow. Same as the flow of excitons in traditional semiconductors, which is very slow as well, and actually impedes a lot of application. But interlayer excitons can actually flow with 0 resistance and with almost super high speed. So this is basically similar to a superhighway, and basically acts as a superhighway for excitons. So, and as a result, this can lead to the formation of superfluidity, which is a different quantum phase. So superfluidity can actually lead to the formation of many different applications like data storage, data storage, then exciton circuits, and many different kind of real life applications. So that's one of the major implications of these interlayer excitons that has been investigated in 2D heterostructures, in TMD heterostructures, and a lot of other emerging 2D materials as well. So thank you everyone for listening. I hope everyone can gain some information from this particular talk as well. Thank you everyone.